What's up everyone, this is Prachurja Biswas and let's move on with atomic structure lectures. And in this lecture, this is gonna be a little more like advanced lecture, a bigger lecture in which I will discuss to you the developments that leaded to the Bohr's model of atom. But before we discuss about the Bohr's model of atom, it is important that we know that what were the factors that led to the development of this model of atom, and these were especially two kind of factors that led to it. And first was the dual character of electromagnetic radiation, which means that the radiation possesses both wave-like as well as particle-like properties. And the second one was the experimental results regarding atomic spectra, which can be explained only by assuming quantized electronic energy levels in atoms. So, before we go into the second and more complex part of it, we will move to the electromagnetic radiation. Today we will understand about the wave and the particulate nature of electromagnetic radiation. So it is known to us that in 1870, James Clerk Maxwell, a British scientist, was the first to give a comprehensive explanation about the interaction between the charged bodies and the behavior of electrical and magnetic fields on a macroscopic level. He suggested that when an electrical charged particle, let's suggest that we have an electric charged particle, let's say an electron, moves under an acceleration, then alternating electrical and magnetic fields are produced and transmitted. These fields are transmitted in the forms of waves called electromagnetic waves or electromagnetic radiation. Before we move on and understand the concept of an alternating electrical and magnetic field, it is important for us to understand that what is an electrical and magnetic field. It is said that if we have an if we have, let's say, we have this particle here and it has some charge, let's say q, then it assume that this q like force applies a force on this charged particle here, let's say it is small q, and it applies some force on this charged particle, and this force divided by the charged particle is the charge of the charged particle gives us the electric field intensity. It is more important to understand the physical significance of it or the practical significance of it. It is said that this charge q here develops an electric field around it like this up to infinite distance, and under this electric field it applies force on any charge kept on it, and that force is equal to the charge on that body into the electric field intensity. And these two are vector quantities because force is a vector quantity, q is a scalar quantity, so electric field is a vector quantity. Similarly is the case of a magnetic field, but in this case in the case of magnetic field, all these things are gone away, and what we have is, let's say, a charge q and another charge, say like this. But what actually is happening here is this charge is moving in this direction, let's say with a velocity of v. Then it also has it also produces a magnetic field outside this, in this area now, up to a direction infinity, and this charge here also assumes a force in case it is also moving with a velocity, say v dash. If it is moving with a velocity v dash, then it experiences some force F due to the magnetic field of this, and this is denoted by B vector. You should know that this force is equal to the charge Q into the velocity B into the magnetic field intensity, and in vector form this F vector is equal to Q into V vector cross with B vector. So before we understand all these electromagnetic concepts, it is important for us to understand the concept of vectors too. So cross vector means that if the direction of velocity is in this direction, if V vector is in this direction and B vector is in this direction, then if we cross this, using the right hand thumb rule and we move our thumb in this direction, then the direction of the force vector will come inside. That is something like this. This is the F vector, but it is going inside the plane of paper. So this is electrical and magnetic field. Now, we have now seen that a charged particle produces an electrical field. We also see that a moving charged particle has a magnetic field. So, electromagnetic theory stated us that when this charged particle, instead of moving with a velocity v, move with an acceleration a, then it produces a magnetic field as well as an electric field, but these are alternating or sinusoidal. Sinusoidal means it is a function of sine theta or a function of sine. So this is what was meant in the electromagnetic theory. It is also stated that the light is a form of radiation which were known from early days, and its speculation about its nature date back to remote ancient times. In earlier days, during the times of Newton, light was supposed to be made of particles. Like if we have a bright ray of light like this, then it was considered to be made up of particles like these, and it was only in 19th century when the wave nature of light was established. Maxwell was again the first to reveal the light waves are associated with oscillating electrical magnetic character. Although the electronic magnetic wave motion is complex in nature, we will consider here only simple properties. To consider simple properties, we first need to look at what does electromagnetic wave look like. So here we have electromagnetic oscillation moving through a space. So we have this big space here, space time. We'll understand the space of time concept, in which I will explain you in a space-time theory explanation which was given by Einstein, but it is really very easy so you can understand that thing. So this is an oscillating electrical magnetic field and is produced by an oscillating charged particle, and it is seen that it is perpendicular to in nature and also perpendicular direction of propagation of the wave. So what we are trying to say here is, let us suppose that I draw like this, and like this. What I actually do is, let this be the x-axis, this be the y-axis, and this be the z-axis. So we see that if this is the electric field in the y direction, as we can see here, if we concentrate on the vector notation that we have, it is in the y direction, and b vector we have in the z direction, then the direction of propagation is in the x direction. Right. So you can see that the electric field is a sinusoidal or an alternating current. The green one is the magnetic field, sorry, and similarly the electric field is also sinusoidal. So the electric field can be assumed to be written in the form of E naught sine of omega into t omega et, and B can be also written in the B naught sine of omega bt. So these can be written like this, right? Also, it is important to know about another vector which is not included in 11-12 syllabus but is a very interesting concept, and is called the Poynting vector. So the Poynting vector gives us the flow of the radiant energy and the direction of propagation. So in the CGS unit or any SI unit, we have the Poynting vector denoted by S vector equal to C square epsilon naught E vector into H vector. Now you may be like thinking about different terms here except this term here, which is very known to us, that is the electric field vector. C is the speed of light. The speed of light. Right. Epsilon is the permittivity of free space. So I'll only write permittivity permittivity of free space, which we will know in magnetism. This is electric field, obviously, electric field, and H vector is called the magnetizing vector, and you should also only know that this is V vector by epsilon, V vector by mu naught. Also, this is not the permittivity, this is the permeability. Make a correction that this here is the permeability, and it is in the electric field, comes from the electric field. Permeability, right? So this is the pointing vector. So pointing is our scientist, so it is pointing vector, pointing vector. Okay, it's called the pointing vector. So this gives us the direction of the propagation of wave as well as the flow of energy. So this is the ray flow or the radiant energy that we have. Okay, but you need to understand that E and H vector are varying. So this H vector is an instantaneous pointing vector. Okay, there is also a average pointing vector, which is denoted by this symbol here. It is noted by this symbol here. This is called the average. These signs are used for average. Okay, whenever you do maths, physics, chemistry, anything, these signs are called as is called the average symbol. Okay, so we have the average pointing vector, and this gives us the characteristic of the detector, the characteristic of the radiant energy that flows. Okay, so this is the half of the electromagnetic radiation. In the next electromagnetic radiation, we will discuss about the characteristic of electromagnetic radiation and the particular nature of electromagnetic radiation.